Registration is open for our 111th annual meeting, and this year's annual meeting will be held on November 4th through 6th in Tucson, Arizona. We will be broadcasting the meeting online simultaneously in order to provide interactive experiences for both in-person and online attendees. Registration for the annual meeting will remain open until October 25th, and remote attendees may continue to register until October 31st. But if you're planning on attending in person, make sure that you get your registration in by the 25th. All right, now we would like to thank and acknowledge our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy. Okay, now let's go back to this title slide here. Our instructor for today is an assistant professor at Queens College of the City University of New York. An expert on white dwarfs and time series photometry, he spent hundreds of nights shooting time series out at both McDonnell Observatory and Apache Point Observatory. He also has extensive experience analyzing data from recent photometric surveys, including TESS, Kepler, and the Zwicky Transient Facility. A couple years ago, he created the Python package Pyriod, which is used for prewhitening frequency analysis of time series astronomical data. If you're interested in analyzing data-mined light curves or doing astroseismology on your own computer, Pyriod may just be the tool for you. Fortunately, we have only the best of instructors here with us today to teach us all about the ins and outs of Pyriod and how you can use Pyriod to do science. Personally, I can't wait to learn more about it, so without further ado, please allow me to introduce our instructor for the day, Dr. Keaton Bell. Welcome, Dr. Bell.
Thank you. Hello, variable star observers. I'm excited to be talking with you. I'm going to share some tools and techniques today for measuring the variability periods that are present in the light curves of variable stars. We're going to do this in a Python environment, making use of some interactive tools that I've developed, this Pyriod package that was just mentioned. So most of this will focus on how to use Pyriod to do what's this so-called pre-whitening frequency analysis process, which I will explain. But first, I'm going to introduce you to the Jupyter Notebook environment for running Python code. So let me share my screen here. What you're seeing is an internet browser. If you attended the last Python webinar, you would have seen how to use Python from the command prompt, as well as how to write and run code that's written in a file. But for this tutorial, I'm going to use this other programming environment called a Jupyter Notebook. That's spelled Jupyter with a PY in the middle for Python. And I brought this up in my browser on my Mac computer by typing into a terminal the words Jupyter and then notebook, and that brought this window right up in my browser. If you're on a Windows machine and you've installed Python with the Anaconda distribution, then I believe there should be a Jupyter Notebook icon in your start menu somewhere that you can just open it right up from there. Jupyter Notebooks are a great programming environment for learning to code, especially because you can write your code and run it in blocks at a time. These code blocks are called cells, and it works all right inside your internet browser. So this is what I see when I open up a Jupyter notebook in this folder that I created for doing this tutorial. It shows all the files that are located in my folder. I've got a FITS file, a CSV file, a PDF, and then this .ipynb file. This is an interactive Python notebook. If I click on this, it's pretty much empty. I've just created one for this tutorial, and I wrote some information up here in just plain text to describe what the goals are for today. There's a little bit of information about this Python package Pyriod, which you can read more about on this link that's used to analyze light curves. So to install Pyriod on your own machine, if you want to do this, you've got to run this pip install Pyriod command in your command prompt or your terminal. That will install the software so that you can import it and use it in Python. And then because this code, it involves some interactive widgets and buttons for manipulating and inspecting your data interactively within your browser. You have to enable these notebook extensions that allow you to do these things. So you would also run these 3 commands after you've installed Pyriod and before you open up your Jupyter notebook in order to get it fully installed. That information is all on the Pyriod website. So this is just some information. I'm going to press this plus sign to insert the first code cell. Here's where I'm going to write Python code. And the first line that I'm going to write is another sort of specific to Pyriod line to help that work and to display all the widgets and buttons that we want to use. It's a so-called magic Python command that starts with a percent sign. I'm going to write matplotlib, which is the plotting library that I use, space widget, and that will allow me to use the widgets that come packaged with Pyriod. And then I will also import the other packages that I'm going to use. The first one, and I'll show you some of the capabilities of this package, is called light curve with a K. That K stands for Kepler, which was a photometric mission that you may be familiar with. This package was originally developed to work with and manipulate and analyze light curves from the Kepler mission, but it's now used for all sorts of light curve data that you could get, especially data from TESS, which I'll show you some of in this tutorial. So we'll import light curve as LK, just to shorten the name of it a little bit. And then for Pyriod, I'm going to import from Pyriod. I'm going to import Pyriod because that's just a little bit nested in there. We could run a cell of code in a Jupyter notebook by holding down Shift and hitting return. And this little asterisk means the code is running. And then once you see a number there, the code has successfully run. So in this environment, it's just like if you had typed this into the command prompt. We've now imported these packages for use. These are pretty much the only 2 packages I'm going to use for this tutorial. There's really not going to be a lot of programming that I'm going to do. We're going to use Python programming to get the data into the Pyriod interactive analysis environment, and then we'll carry out the analysis by working with the buttons that provides. Light curve lets us work with all sorts of light curve data, and it has a lot of great functionalities built in. The one I'm going to show you right now is that it can actually be used to search for and download archival light curve data from the Kepler or TESS missions. And then I'll also show you something great about Jupyter notebooks and why these are so helpful for learning how to program. Is you can use tab complete to see what's available. So for example, I've imported this package light curve as LK. And now if I want to know like what functions light curve makes available to me, I can type the name of the package and a dot. And then if I hit tab, it brings up a whole list of functions that are available to me in the light curve package. So this can do all sorts of things. What I'm interested in doing is searching for a light curve. So I'll click on that. Search light curve function. That's the first, just a super powerful thing about Jupyter notebooks is we can see what functions are available to us by hitting tab. And then the next most useful thing for learning Python is that once you put these parentheses here, as long as your little, the little blinking line is here inside the parentheses, if we hold down Shift and hit tab, I like to hit it twice, then it will show us what the calling sequence is for this function. This lk.search light curve function takes a required argument, which is the target. It's required because there's no equal sign there. And then it takes all these optional arguments. These have default values. And if you scroll down here, you can read the documentation for the function. It tells you what kind of parameters are allowed, what this function is going to return, a search result, and give some examples. So all this documentation is at your fingertips with Jupyter notebooks. I'm going to search for the light curve of a legendary pulsating star, SX Phoenicius. Okay, this is like a high amplitude delta Scuti sort of pulsator. And I run this cell by holding down Shift and hitting return. And this shows me a search result with 11 data products. Okay, these data products are all from TESS data. They're created by different authors. The SPOC products, these are sort of the main TESS pipeline products, but there are also some other pipelines for extracting light curves from the TESS data. And so you can see that those are available here as well. And this star was observed by TESS in Sector 2 and in Sector 29. Sector 29, this was during the kind of the extended mission for TESS. And there's a couple different modes of data. During Sector 2, there was short cadence data where the images were saved out every 120 seconds. And then there are light curves extracted from the full frame images that were read out every 30 minutes. In Sector 29, there was also this ultra short cadence, which is a 20-second cadence light curve. And then the full frame images started to be read out every 10 minutes. So even faster at the slowest rate there. We'll just pick one of these to download. We'll pick the first one, the 120-second cadence data from Sector 2. And so I select this. This is an indexed list of results. I'm going to use square brackets, put a 0 here to select this one, this one product. And you can rerun code in the same cells to manipulate what is available, what's stored in different variables in Python. Here, once I've selected which data product I want, I'm going to press a period. You can hit tab to see what functions are available to me now, and there's a download function, so I'm going to use that one to download this light curve. And here is the light curve data. There's a bunch of different columns of different information. I don't know what half of these are, but the ones I'm really interested in for my light curve analysis are going to be time, right? These are time in some sort of fractions of days relative to some reference date. Flux in physical units of electrons per second, and an uncertainty on the flux error. You see the flux here in physical units is sort of, this is scientific notation. So this E plus whatever says how many zeros have to go on to the end, or how many spaces to move the decimal point. These are sort of in the 200,000 counts level for a light curve. I'm not interested in this analysis in exactly how bright the star is in each measurement. I want to know the relative brightness. How is the brightness varying relative to the average brightness of the star? And so I'm going to do one more thing. The way light curve is written, you can really write these functions with like a sentence, like this is a star that I want to download, and then I want to normalize so that the average value is 1 and the fluxes are relative to that. So here, e to the -1, this is like 0.96. This is 96% of the average brightness up here. Towards the end of the table, this is like 22% as bright as average. So we're seeing this this light curve data and manipulating it in a table. What I really want to do here is now I want to store this in a variable that I'll call LC. So that table with all that data is stored in this variable LC. And then I can pass that to the to the Pyriod package and create a Pyriod object. So I'll call this object lowercase Pyriod. Say that equals capital Pyriod. That's the function I imported from the Pyriod package. And I'll pass to that because in the init signature here, to initialize a Pyriod object, you have to pass a light curve object from the light curve package. That's what we just downloaded. So I'll pass that here. And we've created this light curve object. We can start analyzing this data set. To do that, lowercase Pyriod dot, again, capital Pyriod, open close parentheses. And this displays this interactive cell for inspecting and fitting and manipulating this data set. So we see this beautiful time series light curve here. This is a richly pulsating star observed by TESS. We can zoom in and see the beautiful pulsational variations here. It's just an incredible data set. This is what we are going to fit a model to. What we want to do is measure all of the frequencies that are present in this data set, because the frequencies of variability here are pulsational frequencies of standing waves in this star. And the standing waves in this star, these sensitively probe the interior structure of a pulsating star. And by measuring many frequencies of pulsations from a star like this, we can potentially constrain the structure of the interior and, probe the physics of the interior of this type of star. So that's the science goal for this type of analysis and for acquiring this type of data. But how do we do that? Well, the prewhitening frequency analysis technique utilizes sort of two views of the data. There's this time series view measuring the relative variation over time, but there's also this periodogram view. And in this tab, you see what the frequency content of the data is. So there are all these different lines that kind of stick up from the bottom axis. These indicate that there are significant frequencies of variability at each of these values. What the periodogram does is it tests for a full range of frequencies that these data may be sensitive to. It measures how large of a sinusoidal variation at that frequency would best fit to this data set. So for example, you see that overall there's sort of, a periodicity here. There's something that's generally repeating. Sometimes it gets a little higher, sometimes it's a little lower, but there's a signal running through all of this. That's going to correspond to this highest peak. This is the dominant signal in this data set. This black dot here allows you to select different peaks in the periodogram, and it started at the highest signal. This is in units of microhertz for the frequencies. Those are how many, so those are a million times smaller than a hertz. So this time scale of around 200 microhertz, that's like a little bit more than an hour. You can also set, when you create this Pyriod object, there's an option to change the frequency unit if you prefer per day, or amplitude unit if you like percents or something like that. But this in parts per thousand, 140 parts per thousand, there's a variation at 210 microhertz of about 14% variability. And indeed, we see that these highest peaks reach up to kind of 35% brighter than average. This is the dominant signal here. So what I'm going to do for my analysis is we're actually going to carry out this, this pre-whitening process, which I've created this flow chart for. And we're going to ask ourselves these questions, right? Is there a significant signal in the data? And we're going to ask that just about one signal. Is there a significant signal in the data? Here I see that this peak stands out way above everything else. That is a significant signal in the data. So the answer is yes. This little flow chart tells me to stage this signal frequency for fitting. So I'll show you what that means. That means I'm going to add this signal to my frequency solution. I pressed that button, and that put it into this interactive table that's located under the Signals tab. In the Signals tab, we've now just have these are starting values that came from the periodogram, just the location of the peak here. The frequency is about this. The amplitude is going to be around this value. But there's no measurement for the phase. This is the signal of a sinusoid. A sinusoid has an amplitude, a frequency that it repeats at, and then a phase that just shifts it in line with the data set. These are just initial fit values, but we can actually fit this to the time series data by hitting refine fit. Then this finds the best fit phase value. It also returns uncertainties on the measured frequency and on the amplitude. And because these are such exquisite space-based data, we have really precise measurements of the frequencies. This is 210 microhertz, but it's measured to a precision of, I don't know what this is, a terahertz, I think. So many orders of magnitude signal to noise here. The amplitude is also measured very precisely. And if we go back to the time series tab and zoom in a little bit, because this data set's so long, we see the model that's currently fit to the data in red. And so we see that it is repeating at the right time scale of the main variation that's present in this data. And it's also reaching its peaks at around the same time that the data set here reaches its peaks. That's very good. So sorry, I've skipped ahead in the flow chart. That was the step to refine the fit to the time series. And then we have to ask ourselves another question, similar to the first. Are there more signals in the residuals? Well, let's talk about what the residuals are first. The residuals are what variations remain after fitting this model. That is, is there anything left? Does this model leave anything to be desired for obtaining a perfect fit to this data set? And I would say yes, it does. This model does not produce these very high peaks, for example. We can see the difference between the model and the measurements by plotting the residuals. We zoom in here, we see this is a little different. We've removed the main signal, but all this variation is still present in the data, and we should take efforts to include all of that in our solution as well. If we look at the periodogram, again, looks similar to before, but the signal that we included in our frequency solution is now colored green, and all the other signals are blue. That's because we've included that bit in the model, and that's the periodogram of the model. And in blue, we see the periodogram of the residuals. That's what remains to be fit. So these we can see what's in the model. Our model right now is just a single signal. And in the residuals, there are a number of peaks that correspond to signals that we need to include in the residuals to account for all of the variations in this data set. This little black dot goes to the highest peak in the periodogram of the residuals, and we can repeat this process. So this is ready for us to add to the solution. We can click that button, right? That's in our table here now, and we can refine the fit to that signal. We see that that peak has turned green. It's been moved to our frequency solution, and the time series plot, it's a little peakier now. It's getting a little closer to reproducing those high flux excursions, but it's still not perfect. And sure enough, there are still plenty of signals to be included in our model here. So we continue the process, add to the solution, refine the fit, add to the solution, refine the fit. You see these peaks are turning green as they enter our frequency solution. And we can continue this on and on and on, but at some point we'll need to stop, and we need a stopping condition. So let's see here. So in order to do that, we need to compute a significance threshold. There is this question in the flow chart, or this here about significance, and the fact that we are looking for signals in the data, signals as something distinct from noise. All of our measurements will have some noise associated with them. We saw the flux error column of the light curve earlier. There's uncertainty on our measurements. And if we zoom way in down here on the plot, the periodogram of the residuals, you see the remaining peaks are standing out above sort of a baseline level of just little peaks everywhere, right? These are noise peaks, these really small ones. These represent what's needed. You know, there's a lot of different sinusoidal frequencies that you would have to introduce to your model to not just fit the pulsation signals, but to perfectly reproduce every single data point, which includes the noisiness of the measurement. And we don't want to include that in our frequency fit, because the frequencies that we measure for the pulsating stars, we want to interpret those as the frequencies of stellar pulsations, things that reveal the interior structures of the star. And if we include a noise peak, our noise frequency in our analysis, we could really misinterpret what's going on with this object we're interested in. So we need some way to tell the difference between a real signal peak in the light curve and a noise peak. And the typical way of doing that involves something called significance testing. It involves something called hypothesis testing. We are testing for significance, but to decide whether peaks in this periodogram are significant, we are going to adopt the hypothesis that all of the peaks that remain in the periodogram of the residuals, that all of the whole periodogram just represents noise. Let's just adopt that hypothesis and then test that hypothesis and see if we can reject it. If we can reject the hypothesis that there's only noise remaining in the residuals of our model fit, then we know that there must be some remaining signals in order to describe the data. So the hypothesis that the periodogram here only has noise in it, that implies that most of the variations here, I'm going to hide the model right now, that all of these peaks are at a similar size to each other, and that it's a property of noise in the periodogram that noise peaks pretty much never stick out above more than 5 times the average noise level in the periodogram. So, and that's just kind of a rule of thumb number that I use for space-based data. Some people use different scaling factors for their noise significant thresholds. But what we can do here is we can use the significance threshold functionality to calculate the average noise in a sliding window across the periodogram, and then multiply it by this factor that 5 times the average noise, I'm going to say, that's as high as a noise peak should ever get. So under the hypothesis that this periodogram only has noise peaks in it, I should be able to calculate this significance threshold and see that nothing exceeds the dashed line. Well, this exceeds the dashed line, this exceeds the dashed line. There's all sorts of stuff that exceeds the dashed line. I have to reject my hypothesis that this is just noise in the periodogram. And since I reject that hypothesis, I say, well, then there must be signal. In fact, all of these things that stick out above 5 times the average noise background must be signal. So we can add these to our frequency solution. Sure enough, I'm disappearing these from the plot. They're going into the model. Add this one to the solution, et cetera, et cetera. Now, at some point, the highest peak ends up being very close to 0 in a lot of cases. This is 0 frequency. This is not actually a pulsation frequency of the star, but it's trying to capture a little bit of the very slow variations that are systematics in the TESS data, most likely. So I'm not going to use the frequency here at 1 microhertz that was suggested to me. Instead, I'm going to click over here and select a different frequency to add to my rapidly growing list of pulsation signals. So I can add this one. I can add this one. There's really a lot of signals in this richly pulsating star. We're not going to get to the bottom of this during this talk. I could go on like this for hours, probably finding new signals to include in the model. But what I definitely want to show you is that our model fit to the time series data is really improving at this point. We are really reproducing these variations, and we're building up a large table of pulsation frequencies, their corresponding amplitudes, their phases. We've got uncertainties for all these measurements. This is the kind of data set that we want to produce for these are the type of measurements we want to produce for such a beautiful data set like this TESS light curve of SX Phoenicius. As we add these signals to our frequency solution, we can also go ahead and recompute our significance threshold because we've removed things from the residuals periodogram, and that will lower the significance threshold, making even more peaks statistically significant and worthy of being added to our frequency solution. There are probably over 100 signals in this data set that are significant and that we could analyze to learn more about this star. So I'm not going to add all of them. In fact, I'm going to just stop adding signals and just show you this result. You can imagine the continuing to include additional frequencies will help to fit some of these remaining residuals, which you can also look at in the time series tab. You see that this isn't just noise. There's correlations among these points you can kind of see by eye, although it's getting harder as we go to these really small amplitude signals. See that there's some additional pulsational variability here, but we're approaching a nice measurement of all of the periods for this star. So I've just got a few more minutes, and I want to show you one more thing because this is a AAVSO seminar. I thought I should look at some AAVSO data and especially show you, how you could get your data or any time series data set into Pyriod for analysis, not just the things that are downloadable through light curve. So I'll do this really quick. I already downloaded and sort of manipulated the AAVSO light curve for SX Phoenicius, the same target that we just looked at the TESS data for. I'm going to import just one more package here that I'll use to read in the AAVSO data. I think in your last Python tutorial, you saw how to read in a CSV file, a light curve from a CSV file. I'm going to do the same thing here. Store as a data frame, just using this read CSV functionality, the AAVSO light curve. This is a table similar to the one you saw before. There's dates, there's, well, magnitudes in this case, not flux, there's uncertainties, and there's a bunch of other columns, right? Observer affiliation, somewhere in here is the name of the observer who should probably get credit. And I'm going to pick out the columns that I'm interested in, and I'm going to turn them into a light curve object. So light curve, sorry, first I'm going to pick out the columns I want. This is a date column. I'm going to call this time. And there's also there's a magnitude column. I'm going to convert this to a flux. I'm not going to worry about the scaling factor too much because I'm going to normalize it. So I'm going to take this 10 to the, which in Python is two multiplication signs, 10 to the negative 0.4 magnitudes, I think, I hope, and call that flux. Then I can pass this to an LK dot light curve object with those capital letters in there. This can be passed just a whole data array, or it can be passed the time, flux, and flux error columns. I'm not going to worry about flux error right now because I'm just trying to demo this. It's like time equals time, flux equals flux. You could add flux error if you wanted, but this creates a light curve object. They always have these three columns: time, flux, and flux error. By the way, light curve is a very powerful tool for working with this type of data. So if you want to learn more about that, you can go to lightcurvewithak.org, and they have some great tutorials and demos about the capabilities of this package. I really recommend it. It's a great package. It's really made doing science with light curve data a whole lot easier. And it's what Pyriod uses behind the scenes very much to do its calculations. I'm going to call this LC2 because we already have something called LC. And I'm going to pass that to something I call Pyriod2 because we already have a object called Pyriod, lowercase Pyriod. Pass LC2 with that and look at the interactive Pyriod tools. Now, this isn't all the AAVSO data that's available for this star. I just selected 2 nights of data where there was quite a bit of measurements for this star, and I selected just the V-band filter. You know what? There's one more thing I want to do here. I'm going to normalize this light curve, and then I'm going to pass it to Pyriod2 and redo this. So now it's kind of relative variations compared to the average. If I zoom in, you can see what the AAVSO data captured on the first night. Sort of, this is about 2 hours of data, probably captured a couple of cycles of the main pulsation signal. And then about 30 days later, there's about a cycle and a half that got captured here. So, well, the data quality during the observations look quite similar to the TESS data quality. And the duration of the light curve is about the same. There's obviously many days without observations here, which is going to make this data set more difficult to analyze, as you're about to see. Because if I look at the periodogram here, these peaks look way wider. There are peaks that stand up above the background of signals, but each of these features are sort of filled in a little bit more compared to up here, where when we looked at the periodogram of the when we looked at the original periodogram, the highest peaks were like razor thin because they're so precisely measured with so much data. These peaks are much wider because each observing run was only a couple hours, and that kind of sets the width of these signals. That's sort of how precisely we could measure these frequencies. It's pretty limited by how short each individual visit to the star is. If we zoom in here, see there's a little bit more going on. And if we zoom in even further, we see that there are actually these sort of like a lot of peaks all over the place, like a big zigzag pattern. And you could pick any of these highest parts of the periodogram to add into your frequency solution. And the problem is knowing which of these to include. If we pick the highest one here and we add this to our frequency solution, we get a fit, a very precise error. In this case, this doesn't really represent the uncertainty because it only measures the sort of the width of this one particular peak. It's how precise we could measure this signal if we knew that this was the correct peak. But you see that what's gone into the model, even though we only selected one peak to include in the model, in the periodogram of the model, that has taken away the power from all of these peaks that exist here. And that's because each of these peaks basically represents the same signal. They fit very nicely. Any of those frequencies would fit the main variation on this first night of data quite well. They would each fit the main variation out here quite well. But all those peaks appear because of this huge gap that we have. We don't know, because we weren't looking, exactly how many cycles of pulsation we missed during those 30 days when observations were not being taken for this star. So that's what each of these peaks corresponds to. You know, there are many hundreds of cycles that we missed, and there's a peak here that corresponds to missing, say, 400 cycles when we weren't looking. And then there's a peak that corresponds to, say, missing 399 cycles and 398 cycles, 401 cycles, 402 cycles. And that's something that our data are not sensitive enough to tell the difference between. So the highest amplitude signal that we found here, the one that was just automatically selected, was 217.9. So let's say 218 microhertz. From the TESS data, where we didn't have the problem of all these peaks are called alias peaks. Over here, the ones they're very small and right next to the main peak. Here we were able to measure that the strongest signal was at 210.57 microhertz. So that must be the same signal that we're looking at, but we picked out the wrong alias peak in the periodogram. I'm going to delete this from our solution to go back to the beginning, where you can see where all of these different peaks are. I'm going to look because one of these is going to be, I think this one here, at 210.57 microhertz. That's matching the signal that we measured so precisely from the TESS data. So when you're looking at ground-based data, this is the big challenge. If you want data that spans a large baseline so that you can measure the periods that are present very precisely, but you also don't want very large gaps in the data because that limits how accurately you can measure the pulsation frequencies or whatever frequencies are present in your data, and that affects how good your results will be. So without any other data, it would be impossible for us to choose any one of these frequencies as being the most significant. But because we can reference the TESS data, which was able to resolve the correct signal, we can confidently add this frequency to the data set. And then we could go and look for additional significant signals in the residuals. In this case, I think it would be difficult, again, to pick out which of the many peaks that are part of this set of signals is potentially the real one. So I'll show you one last thing that Pyriod is capable of. Maybe some of you with keen eyes notice this. The first frequency I added was 210.57 microhertz. The second frequency from the TESS data was 421.14 microhertz. That's 2 times this value. So I sort of misled you. This is not actually an independent pulsation frequency. It is a signal of the pulsations, but because it's exactly twice this frequency, we call it a combination frequency or a harmonic signal. It doesn't represent an independent standing wave pulsation frequency in the star. But knowing something like the second strongest peak in this star has a frequency of exactly twice the strongest peak, it gives us a way to pick out the correct signal in the AAVSO data, where there are normally many candidates. We can pick out the one that's twice the signal that's already included here, or with Pyriod, we can actually just define the frequency to be mathematically related to the frequencies that are already here. We could call this 2 times F0, and we can add that to our solution. So this F0 and 2 times F0, this frequency is always going to be exactly twice this. If we type refined fit here, we get an improved fit to the time series, which now fits a little better than it was earlier. And beyond this, I think the AAVSO data, it would be difficult to measure any frequencies reliably beyond that, but we've captured the 2 main signals that are present here from just a few hours of data separate, over the span of a month. So that's everything I wanted to show you for this talk, but I welcome your questions. And thank you for joining today.
Thank you so much, Dr. Bell. That was an excellent presentation, very clear. Okay, we have had several questions come in here already. So let's start with this question from Charles Cinnamon, who had asked about aliasing specifically with regard to TESS data. Is that something that someone needs to be careful to care about and understand when working with space-based data?
Yeah, it is. So I mentioned a little bit about aliasing at the ends. It's not exactly, I think, what was being asked, but this issue where a single, this is like a tongue twister, where a single signal it can cause multiple peaks, right? There's only one frequency in the data, but it's causing there to be like, I don't know, 1,000 peaks here or something, right? And selecting the right one is one of the main challenges of doing this type of analysis. Now, that's not as much of an issue. This particular type of aliasing that comes from the large gaps in the data, that's not so much an issue for TESS. But there's another type of issue. Let's take a look here. There's another type of issue potentially in the TESS periodogram. I'm going to recalculate this periodogram, but out to a higher frequency than I did originally. I let the program kind of pick a good frequency to use. Let me see if I remember how I even wrote this. I just after. So restarting this analysis, if we look at the periodogram now, I've calculated it out to a higher frequency. And you see more peaks out here at the really high frequency. This is called Nyquist aliasing, and this is where you need to be concerned a little bit that at least the data rate that you're getting, that the cadence of the data or the time spacing between the data is sufficiently fast to resolve the time scales of variation that you're interested in. So if a star varies, I do a lot of work with pulsating white dwarf stars. So say pulsating white dwarf stars vary on time scales, between a couple and maybe 10 minutes, something like that. So let's say a star, we know a star can vary as fast as every 2 minutes. We know the type of variable we're looking at, the time scales that might be relevant. If the star can vary as fast as every 2 minutes, we need to make sure that we're measuring these peaks, that we're sampling that time scale of variation, which means to sample that well, we need to have at least 2 data points per period, so that we see the data both go up and then back down during that brightness variation. If the data aren't sampled finely enough, then we might not be sensitive to that. What you're seeing here is what's called Nyquist aliasing, where every signal, like this signal, is mirrored over here. This is another peak corresponding to the same signal. This is another peak corresponding to the same signal. Now, because of this duplication of peaks, by default, Pyriod only shows you the periodogram up to the highest frequency that it would be sensitive to, that the data are sensitive to. But if the highest frequency the data are sensitive to is not as fast as the frequencies that are present in the data, then what you see in the peak that shows up in the periodogram is a so-called alias, that the real peak is up here in the high frequency part of the periodogram that isn't usually where you're searching for signals, but you probably identify the low frequency alias and fit that instead. I think Pyriod doesn't do a great job of showing you what these high frequency fits are. You saw what the fit at low frequency looked like. I'm going to try to fit this signal and just see what it looks like in the time series tab. It's a little undersampled here. When I fitted it originally, you saw it kind of follow the main variations here. Right now, what it's trying to do, and it's not sampled finely enough, but it's basically between every data set, it's going through a big dip. It's because you're not constraining those frequencies of variability. So it's like it fits through the point, and then it wiggles, and then it fits through the next point, and then it does a wiggle, and then it fits through the next point. And if you pick the one that was up here, it'll do a couple wiggles. But you saw when I added this signal to the frequency solution, it's not only this line that turned green and disappeared, this one went with it, that one went with it. If you calculated this to way higher frequency, you would see additional peaks that are aliases as well. That's a great question. Aliasing is a concern. You want to make sure that the data sampling rate is fast enough for the variations you might be interested in. And that's why when I first looked at this set of light curves that we could be interested in, I picked the 120-second cadence data instead of the half-hour cadence data, because I knew we would need this faster data set would be more sensitive and more accurately represent the variations that are present in this star.
Great answer. Thank you. Okay, let's see. Next question here. This one comes from someone who says they're a physics undergraduate student currently doing a project all about searching for periods of binary stars. And for their project, they've been using Loam-Scargill to do the Python code. And they would like to know why you would choose light curve over Loam-Scargill.
This is a Loam-Scargill periodogram. So the type of periodogram that's being calculated here, yeah, I didn't use those words. There's the time series. I regret doing what I did here, but yeah, this is the Loam-Scargill periodogram of this time series data. So I think maybe that answers the question. And it's computed right out of light curve. So there's like LC2 is a light curve object. The light curve with the K package is great. If I hit tab and see what functionalities are here for manipulating this light curve object, one of them is 2_ periodogram. And if I put the parentheses here and look at the documentation, the default method for computing the periodogram is lomscargle, and this is the function that I call behind the scenes in the Pyriod package. So yeah.
Okay. Makes sense. Thank you. Okay, and next question here. This one comes from Richard Wagner, who says, excellent. I can't wait to move on to this from period 04. When analyzing a star, would it be correct to manually input a bunch of the harmonics of the main frequency and then proceed to find possible other pulsation modes that way?
Yeah, I like that idea. Richard. And this is my homage to period 04. I used period 04 in my research extensively. And then I kind of moved to Python as that became more popular for doing research. And I felt that a period 04 like program was really something that was missing. And, Python is so great because people make available the tools that they're working on. So we've got things like AstroPy, light curve package, and now Pyriod is my little pre-whitening contribution to that. So I just like the tabs here, you may have noticed, this is kind of similar to the period 04 setup. So I was trying to replicate that. I think it is a great idea to try to input a bunch of harmonics. I usually do it the other way. I usually fit all the signals that are present. And then once I have a big table of signals, I sit down and I look and I try to identify, okay, this looks like a harmonic. This looks like because it's not just harmonics, like multiples of a frequency. Sometimes there are combination frequencies that are sums or differences of multiple frequencies. So you also have to look for that. Yeah, you could start as you go. That's a great way to do it. Because what I usually do is once I have the fits in here, I do actually want to fit them in the model where I'm enforcing that the harmonic frequency is always exactly twice or 3 times or whatever the base, the fundamental pulsation frequency, or that the sum of frequencies, that it always is exactly the sum of the involved frequencies. And so I would prefer to write these in here. Like I've added this frequency, I would prefer to put the next one as 2 times F0, add that because we know that's the next highest peak. That's caused this signal to go away. We could look for, we could even, sometimes I do it this way, 3 times F0. Let's see, if I add it here, it'll put a little box there, and sure enough, there's one right there. So the best way to include this peak in our solution is as a 3 times F0. We could refine that fit. And as we fit other independent frequencies, we could also try things like, let's add this next peak here to the solution. We could explore to see, okay, I wonder if F0 plus F1 is present. We can add that to the solution. And before we fit it, we can just look to see, oh, yeah, that's this one here that's still blue, but has the little diamond on it. And in fact, all these orange diamonds indicate the combination and harmonic frequencies that are defined arithmetically. And the green diamonds are the independent frequencies. So since this peak stands out above the noise, I would, prefer to include that as F0 plus F1 and fit it that way. Great question.
Great answer. Thank you. Okay. Let's see. So Joyce Guzik had a question, which I think is pretty related to what you just talked about. Does Pyriod have a way to find all of the combination frequencies?
It does not currently have a way to find all the combination frequencies. It's a bit challenging, a lot of potential combinations, but it's something I have in mind to try to implement. It would be a really nice feature. So yeah, possibly in the future, we could try to do something like that.
Okay, thank you. And next question here. Are there any tutorials for installing Pyriod from GitHub, since a lot of us here are not actually familiar with installing packages in that way?
Yeah, well, you don't need to install it straight off GitHub. You could, as you're right, I'll click on the link here and show you what this brings up. So GitHub is a place to store software and to distribute software. And you could download it directly and install it with this setup.python function, but I recommend this is also available on a package manager, pip. So you can just type in your command prompt or your whatever you call it on Windows, the PowerShell or the terminal, depending on what type of computer you're on. You can type this pip install Pyriod line into your command prompt. That should install Pyriod for you. But be sure to run these functions as well to enable the widgets. And also you need to type this line as the very first line in your notebook, this matplotlib widget with the %sign. Otherwise, all of this stuff will not display. And so you'll run your Pyriod cell and this stuff just won't be here. And so it's very important to install this correctly. So those are the installation instructions. You can read them here. And it should just be these few lines: pip install Pyriod, and then this. And to your more specific question, this is how you would install it if you wanted to download the version on GitHub. You could download a zip file of the package and install it this way, but I really don't recommend it.
Okay, thank you. That helps clear things up. Okay, let's see, we have time for, I think, about 2 more questions. So we had a question come in here from Ed Mullen, who asked, so all of these patterns that you've been finding and fitting, what are they physically related to? What's actually going on in the star to create this?
Yeah, these are well, I'll be honest, this isn't the type of pulsating variable that I usually work on. It was just a very nice, rich data set to show you. But so a little out of my depth here, but this is a pulsating variable star. So each of these variations, or more specifically, the variations that are not these combination frequencies. So in this set of signals here, this peak is a pulsation frequency. It is a resonant frequency of this star. It's like if the star were a bell and you were to ring it, this is a tone that you would hear, right? And just like with bells, if you were to ring like a small jingle bell and you were to ring a big old gong, those sounds would be really different. Those frequencies are very sensitive tracers of the physical configuration of the object. And so when you hear a bell ringing, right away, you probably have an idea of like, oh, someone's ringing a small little bell, or someone just rang a big old gong. You can, right, you're doing this frequency analysis in your head, right? And you're inferring something about the physical object that's vibrating. We try to do the same thing with these pulsating stars. But these objects can vibrate in many simultaneous frequencies that really help us to study and constrain the physical properties of these stars. So here, this peak, we're measuring one of the resonant frequencies of this object. Here, we measure another resonant frequency of the object. These peaks, these yellow diamonds that are the combination frequencies, those have something to do with the interactions between these modes, or the ways that these modes both affect the star as they ring through it. And so these are not independent pulsation frequencies, but these two are independent resonant pulsation frequencies. That's why it's important to identify the harmonics and combinations and distinguish them from the, I'll call them the parent mode frequencies, because the parent mode frequencies are the real, bits of information that we want to know about these stars.
Thank you. Very interesting. Okay, and let's see, one more question here. This one came from Enrique Boneker, who asked, so how should you take this set of frequencies that you've determined and then convert that into information about the period or set of periods that are dominating a star? So
yeah, absolutely. A great question. I should have mentioned something about that. So the typical relation between frequency and period is that the period is 1 over the frequency. So if something happens twice per day, that's a frequency. Well, that happens every 12 hours, right? 1 over 2, where twice per day was the frequency. Same thing here, but the units can be a little strong or a little strange. Microhertz, it means how many millionths of times per second did something happen. I think that's right. But Pyriod does convert that. These are not available right here in the signal table. We have frequency listed, and the errors are in the same units, but you can access another table that has a bit more information by doing Pyriod. That's the name of this Pyriod instance. Pyriod dot, and I hit tab to see what's all available here. There are some functions that allow you to use Pyriod just by calling functions instead of clicking on the buttons. But I typed Pyriod dot fit values is this table. It has the different names of the frequencies, whether they're included in the fit, frequency, uncertainty, etc. And period. This is in seconds, and the uncertainty on the period also in seconds. So that's how you would do that. And if you go through and also do a calculate a significance threshold, right, which I've just done now and added down here is the red line at the bottom, and you look at this table again, it'll also tell you what the signal to noise ratio is for these signals, given that significance threshold. This is how many times larger this amplitude is relative to the average noise in the periodogram, at least given the signals that you've adopted already. Yeah,
great.
Thanks for asking that. Yeah, periods are sometimes easier to think about.
Well, great answer. Thank you. Okay, and let's see. I know I said that was the last question, but we had a quick one come in from someone who's interested to know if you will be presenting any other public lectures on Python in the future that he should put on his calendar.
I don't have any plans to right now, but I have been working on writing up a paper about Pyriod and, like an in-depth user guide that explains, all of the functionalities. I was only able to get into, the main ones here. But there will be a paper in the next few months that comes out describing what all the functionalities are, maybe, some of the things that you need to think about when doing this type of analysis, what to take care about, what to be concerned about, more advanced use cases. And once that paper is published and available, I'll add a link to it on the Pyriod GitHub page here under the this little bit of documentation.
Great. Well, we'll have to keep an eye out for that then. Thank you.
Mm-hmm.
Okay, and I saw there were a couple of questions for me asking if the recording will be uploaded to YouTube later, and the answer is yes. You will all be able to review this excellent instruction later once it goes up on YouTube. And the recording is also available immediately on our Facebook page as soon as the webinar ends today. So if you want to go back today, you can do that by going to facebook.com/AAVSO. Okay, and with that, we'll go ahead and close the Q&A, start with the ending announcements, the most important of which is that I would like to extend an enormous heartfelt thank you to Dr. Bell for sharing his time and his knowledge and expertise with us today. This has been wonderful. Thank you, Dr. Bell.
Yeah, thanks, Lauren. Thanks everyone for coming. A lot of people. I'm glad this was so well attended.
Me too. Okay, and then let's see, wrong slide. Let's go to the end here. There we are. I would also like to thank again our sponsors before we close today's webinar. Our sponsors are Boise Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy.